I wanted to, I know, just whirlwind tour of all of this stuff, to introduce one more idea, and I can also, probably when we're done, introducing this in a video as well, since I think we're not going to give it justice in our time here. But this is to bring in the idea of these beta dicarbonyl compounds. So remember here that if we have a base, we can deprotonate this, supposed to be an O, compound to generate our enolate. Not sure why I left all this space here, so let's just put this down below. And if we have this hydrogen here between these two, we'll use the same thing, carbonyl compounds. Oh, I think it was the draw resonance structure. So we can then deprotonate here, and form another enolate. And this beta dicarbonyl compound is much more acidic than the original one, because now we can draw resonance structures where this negative charge is delocalized throughout both of these oxygens. And that was on the video. The jargon here is that let's just take the carbonyl on the right here in the top and then use the language. So this is the alpha carbon to the left, and this would be the beta carbon. You can do the same thing starting from here, it doesn't matter. And so you see that the other carbonyl group, or the relationship between them, is they're at the beta position. So one is here and another carbonyl is at the beta position. So the jargon is beta dicarbonyl. These are actually very useful compounds, these dicarbonyl compounds, because of this low, or this relatively acidic proton with a low pKa. There are a lot of reactions that one can do with this sort of a compound, this beta dicarbonyl compound. So number one that's shown here, we could just directly alkylate this. And this is what we've already seen. So we could take sodium methoxide, deprotonate this, and then an SN2 reaction, say add this ethyl group here. Now there are two classic reaction sequences that use these beta dicarbonyl compounds. And this is the last thing I wanted to show here. They're known as, one is the acetoacetic ester synthesis, number two, and number three is known as the malonic ester synthesis. These are very similar, but the difference is in this compound that you use, the beta dicarbonyl compound. The first one here uses this compound, which is known as ethyl acetoacetate, or it's an acetoacetic ester, which is where the name comes from. Notice it is an ester and then a ketone. The other one, malonic ester synthesis, has a compound that's a diester here. And this is known as diethylmalonate. What you end up doing is you take some, say an alkyl halide, that's where X is chlorobromoiodo, for example, and you react this in a multi-step sequence here with, let's say, this ethyl acetoacetate. And we end up having our R group, and we've added a methyl ketone. So we have this R from here, and we have 1, 2, 3 carbons that we've added, and it's a methyl ketone, which is going to come from this part of the compound. The malonic ester synthesis, again, we can take an R group, and what we end up doing is we add 2 carbons, 1, 2 carbons, and a carboxylic acid as well. So these reactions occur through multiple steps, and they're useful for adding these groups onto some alkyl compound that you'll like. So let's go through one of them here, and then we'll highlight there. We've seen everything already in this sort of reaction, except one key reaction, and that's what I want to make sure that we have time to talk about. So let's take this acetoacetic ester and carry it through the synthesis. And overall, here's going to have 5 steps. This is one variation of it. And our key alkyl halide is this propyl bromide here, or bromopropane. And so we end up having 3 carbons here, and we've added 1, 2, 3 more carbons and a ketone. So let's see how we could actually come up with this. Let's start with our beta diketone, or ester here, beta. And also I should say now, the jargon here is this compound, this is green here, is known as a beta keto ester. And and these are related to a lot of also biocompounds that one will see, is that this is an ester, is a functional group, and then adjacent to that, here's the alpha carbon, here's the beta carbon. There's a ketone or a keto group, and so it's a beta keto ester is where the name comes from. So in the first step, it looks like we're going to take our base, sodium ethoxide, and ethanol. So probably going to act as a base. And so we have 2 protons here between the 2 carbonyl groups. We also have 3 protons out here. However, because of the resonance stabilization, and if you're interested in the pKa values and such, that's all in the video. I tried to sleep it there. This is going to be much more acidic in terms of this proton, one of those 2 compared to the 3 over here. So let's deprotonate that proton that's sandwiched between the 2 carbonyl groups. And we could write resonance structures now where we delocalize these electrons across the system. And also, there's an interesting point, hopefully on the video, where I talked about very briefly the difference in pK of an ester versus a ketone or aldehyde. But now for this reaction, our next step is, looks like we have this bromoalkane. So in an SN2 reaction, you can kick out the bromide. So this is alkylation. We're forming a new carbon-carbon bond. 1, 2, 3, down below. All right. So now the key thing here is this compound here on the right that I'm circling. And if we compare it to our product, it looks like this area over here on the left is our final product. So now we need to somehow get rid of this group here, perhaps. We have 3 steps. Looks like we have sodium base. Number 3, number 4 is acid, and number 5 is heat. Now, in the presence of base, let's see what we can do. Well, let's take sodium hydroxide. This is in the presence of water and also heat. See what sort of a reaction could happen. Well, we could have the hydroxide take a proton off. However, now we also know that with hydroxide, if the heat helps this, is that we could go back to our reactions with carboxylic acid derivatives. And the hydroxide, it could attack the ketone and form a hydrate, but it could also attack the ester. Let's see what happens there. So we'll write out this step. So this is all the same. And what we've done now is let's have the O minus, OH. So we're going back to our reactions of carboxylic acid derivatives. And we have a leaving group here. So we can go ahead and kick out ethoxide. Let's go this direction. This part is all the same. And what we've done now is we've reformed our carbonyl group, and we've actually generated a carboxylic acid. So what I've done here on the right is I'm reforming the carbonyl group, kicking out ethoxide. So this is hydrolysis of an ester under basic conditions. So it goes back to our previous carboxylic acid derivative chemistry. Now, we have a lot of base around, whether it be hydroxide or ethoxide. That's just going to go ahead and pull a proton off here. And we don't want this to happen necessarily, but it just does because of the acid-base chemistry. So you end up with this species. Now, we have in step 4 acid around. So we're actually going to now acidically again, quench this base. So let's go ahead and protonate. And actually, I'll go down here, save some space. So now we have this species. And going back, actually I'll make it a little bit smaller for a minute so I can show our product, again, now looks like this part over here on the left of the compound. Looks like way up in the upper right here are 1, 2, 3, 4, 5, 6 carbons. The carbonyl group at 2. So if I start down here in the bottom left again now, so 1, 2, 3, 4, 5, 6 carbons, so it actually matches. But we need to remove this carboxylic acid. So Yes, Kyle. One of the things here is this makes it look like I want to just draw lots of structures, which actually is partially true. This compound here that I'm circling in the middle of the second row, and this compound over here on the far left are the same thing. What ends up happening is this reaction is first under basic conditions, so we have hydroxide over here in the far left, so that once you hydrolyze the ester, generate this carboxylic acid, it just gets deprotonated. You don't want that to happen in the end, but you can't stop it because you have base around. So what you end up doing is you add acid. So it gets deprotonated, which you do not want, forms the conjugate base. But then when you add acid, you get back what you actually want. Okay? And the reason you want this is that when you have this compound here, when it's protonated, this actually undergoes what's known as a decarboxylation reaction. This is the one new step. So first of all, I will put it here. This compound here has a carboxylic acid. So next to the carboxylic acid, we have an alpha group. There's our beta carbon, just for the name. So this is a beta keto acid. And these are known for undergoes, let's not spell that, decarboxylation. Which is a real word, I think. And it's removal of a carboxylic acid. So we need to get rid of this carboxylic acid. And this occurs under this mild acid, and the heat helps promote this. So how can we need to break this carbon-carbon bond, and it looks like we could remove this maybe as carbon dioxide, as CO2. So I'm going to scroll up just a little bit, I'll make this bigger again. Let's rewrite this group to help show how this happens. So I'm going to take this compound and just use this little oops. This is technically not right. We'll use like a little loop-de-loop arrow here. And what I'm going to do is actually rotate around this bond here. These are all sp3, this is an sp3 hybridized carbon in the middle. So we can rotate. And hopefully this will make sense when we go all the way through it. So I'm going to keep the carbonyl group on the left. And then there's our group we have down. And what I'm going to do is take the carbonyl, the C double bond O, and put it over here to the right. And here's our oxygen. And there's our carboxylic acid. So all I've done is rotated here. The reason for doing this is that this will help show how this reaction may actually occur. So what we need to do is to break this carbon-carbon bond, and if we could form carbon dioxide, that should be energetically favorable. And in a six-membered transition state, what we can do is actually pull a proton off to the CO2 here, form carbon dioxide, but now we would have too many bonds to this particular carbon, but we can then use those electrons in this carbon-carbon bond to form a new carbon-carbon bond. So there's a lot happening here all at once, but what we're doing is we're using electrons in this carbon-oxygen double bond to form a new bond to the hydrogen. We're breaking this oxygen-hydrogen bond here to form a new carbon-oxygen double bond, and we're breaking this carbon-carbon bond to form over on the left, a new carbon-carbon bond. Let's see what that gives us. So for the left compound, now we haven't done anything with our group dangling down here. We've formed a new bond between the oxygen and the hydrogen, and we formed a new carbon-carbon double bond here. Then on the right, we have carbon double bond to oxygen, double bond to oxygen. So that's carbon dioxide. So that's great, that's stable. And then what you'll notice here is we've actually generated an enol. Here, so this is our enol. So on the last step, what we can do, since we're under acidic conditions, is we can actually have this enol tautomerize, to form the tautomer to the to the keto form. So if we were to have this species here, so I'll kind of go underneath. So we'll go down to the bottom here. We'd end up having this. What I'm going to do is write this in a more conventional way. And then last, we'll regenerate our acid. Oops. Let's just go to the right again. Oh, somehow it turned that oxygen and drew a circle. That's the best one I've drawn in the past 4 weeks. Comes in the last day. That's amazing. I wish I knew how that happened. Okay, so let's go back. It's a long reaction mechanism. I'm sure we're getting winded of all of this new chemistry, but let's see if it makes sense. I'll scroll up for just a second and then I'll scroll back down. Overall, this acetoacetic ester synthesis has multiple steps, but we can take this compound that's shown here on the upper left, this ethyl acetoacetate, which is the common part of this mechanism, common reagent. And here we happen to use this alkyl bromide. We'll see there's a lot of different structures that you could use. But in the end, we've taken from our 3 carbons of our alkyl bromide, which are these 3 here. We've added these 3 carbons. 3 carbons and the ketone. And then this over here was what comes from the alkyl bromide. So we needed to come up with a mechanism for that. So I'll scroll back up now. And a number of steps, and this combines older and newer material. We start with this relatively acidic beta keto ester. So our base is going to deprotonate this on the left, generating our enolate ion, which in an SN2 reaction, just like we were talking about with kinetic and thermodynamic products, is going to get alkylated, in an SN2 reaction, kick out bromide. So we form a new carbon-carbon bond. Now we have a lot of acid-base chemistry that goes on to get rid of this ester group here. The first thing we do is hydrolyze it, going back to our chemistry with carboxylic acid derivatives. And we drew the mechanism out here of the tetrahedral intermediate, kick out the leaving group. Now there's a couple of steps that complicates things. Is some unwanted acid-base chemistry because we end up pulling the proton off here, but we really want the proton on here. So then we have to then acidify the reaction. So the proton comes off, forms this intermediate, put the proton back on, and now we have this compound over here on the left side, which is known as the beta keto acid. It's a carboxylic acid. We want it protonated, and we want it protonated for this decarboxylation reaction. It has a keto group at the beta position. This is the new step, and this oftentimes, it will happen spontaneously. So it's quite energetically favorable to happen because you release carbon dioxide. And you push the reaction oftentimes by adding a little bit of heat. So just add some acid, protonate your carboxylic acid, and then turn up the heat. And what I've done here is to show how the reaction can occur. Rotate it around the purple bond, here the purple arrow, to show that there's a lot happening all at once. But what we're ending up doing is we're forming our enol on the bottom arrow here. We're releasing carbon dioxide, and this is forming the oxygen-hydrogen bond. Once we formed our enol, then we're back to enol keto, now tautomerization from the beginning of today, and that ends up forming our final product. So I apologize for rushing through this a bit here at the end, but hopefully you can see in this multi-step reaction how it builds on a lot of the things that we've seen and then introduces this idea of decarboxylation. Now, I'll go back up a little bit for a minute. It'll be good to practice this before your next exam and see some of the variations. Another one is this malonic ester synthesis. It's the same idea, except notice you have 2 esters. And so what you will end up doing is hydrolyzing both of them to form 2 carboxylic acids. And one of them will be lost. It doesn't matter which one because they're both the same. One will be lost is in that decarboxylation reaction, and that's why you'll end up with a carboxylic acid in the end. But if one lines up these two reaction mechanisms, or I should maybe point to the left, the overall synthesis, you'll see the parallels. One other really fun aspect of this reaction is that we just added, I'm sorry, I'll just scroll back down again. We just added this one kind of boring propyl group here in step 2. You have over here on the right, I'll circle, after we've added the alkyl group, there still is a hydrogen here. So a lot of times what you can end up doing is adding a second group. Could be a propyl group or maybe some other group that you want to add. So you can actually add 2 different groups in this acetoacetic ester synthesis or with the malonic ester synthesis. Or one of the other exciting things is if you have a dihalide, so back right here at step 2, you have, say, 2 bromines, maybe more carbons in between, 2 bromine, you can actually generate a ring here. So there's a lot of variations of this, but it's all mechanistically, it all follows what we've already seen. Okay, go up the previous page. James, do you want this one or the one before? The one before, maybe this one. Okay.